In this video, I'm going to be doing a bunch of practice problems on testing infinite series for convergence. I've done a video in the past before on how I think through these types of problems. Like once you see a series, what are the things that you should be thinking of? What are the clues that tell you which test that you should try? So I've done a video on that. I would recommend that you watch that first before you come to this video, because in this video, I'm going to go quite quick. I'm not going to be slowly going through that checklist of things to rule things out and all of that. I pre-solved all these problems, so usually I go a little quicker. And I'm filming this more so to hopefully help you, if you're a student at UCI Math 2B, to see the possible types of problems that they could ask on the final exam, because I took these problems from an old class at UCI that no longer exists, the old class where they used to teach infinite series, Math 2J. So I took past exam problems or study guide problems, and they're here in this video that I'm going to work out, or I'm going to explain my thought process quickly. So again, if you're stuck on how to think through these problems, watch that other video first. And the intent of this video is to see possible types of problems that can come up on the final exam. Whether you're at UCI or not, these are pretty typical questions in my opinion, that you can expect if you're taking a calculus class that involves infinite series. Okay, and of course, if you want more practice after watching that other video, this can be a good video to just see more practice problems and get the practice in. So with that said, as always, I would recommend that you try the problems first by pausing the video and then unpause it to see my solution and how I think through the problem. Again, I'm going to go relatively quickly, so you can slow down the video if you need to. You can pause to look at the small details of my work and all that. And of course, if you have further questions, you can leave it in the comments. And one more thing before I begin, I can't guarantee that all my answers are 100% correct. So if you spot an error or you think there's an error, please leave it down in the comments as well and I'll address it. All right, let's begin now. First, we have this series. Does it converge? Does it diverge? So immediately here, I'm eyeballing. There's an n power, so maybe root test, but maybe test for divergence as well. Actually, test for divergence would be hard, because actually, it would work. Would it not? Test for divergence, because as n goes to infinity, this term would go to 0, but we have 3 to the infinity. That's going to diverge. Okay? I guess here I use the root test. So again, what am I trying to say? There's multiple ways that you can approach these. So I guess in this, when I was typing this out, I thought root test, because as I said, something to the n power, that's probably root test. But actually, as I saw the problem once again without seeing my answer, test for divergence is much easier, actually. And it shows that the root test also shows that it diverges. Okay, so that's my answer there. Next, how about this series? Does it converge? Does it diverge? Again, immediately I see test for divergence. If the limit as n goes to infinity of this guy is 1, not equal to 0, so it diverges. So use the test for divergence whenever you can. It's the easiest test. You just have to eyeball what the limit is. This one was really easy because it's a rational function looking like series or sequence. So it's easy to take the limit. This one was quite obvious as well. Once I saw it again, as n goes to infinity, it's 3 to the infinity. It's like 3 to the infinity. Okay, how about this one? So go ahead and try it first. Immediately I see this alternating sign, so maybe the alternating series test, but also I can rewrite this a little bit to make it a geometric series, is what I'm seeing right away. So that's what I did, actually. It's the alternating series, because that might not get us anywhere. I didn't do it here, but I do see that I can write it as a geometric series in which I can find the sum, actually, if I really wanted to, if it converges. So I can rewrite this as minus 3 to the n times minus 3 to the first power. Okay, now this is a constant. I can move it out. Okay, and then this is to the same exponent, so I can write it as minus 3 over 4 to the n power. And this, for a geometric series to converge, the common ratio, the absolute value, should be less than 1, which it is. So this converges. Okay, Oh, that's it for this number. Okay, so I feel like I said this in that other video. If you watched that video before here, doing these quickly comes with experience. You just got to do a lot of these. So that's when you see patterns like this one. That's how I got good at them, honestly. I saw patterns. Like if it's something to n power root test, like this, I can use some algebra to rewrite it and it'll look more familiar. This one, I could immediately take the limit, or I could probably use the comparison test, the limit comparison test, or something like that if I really wanted to. Okay, so if you're not good at these, again, I would recommend, once again, watch that other video first to hopefully see my thought process. Maybe that can help you out. And then practice a lot of problems, and then you'll just get better with practice, hopefully. Usually that's the case. Okay, next. Here, how do we test this series? Immediately, I see, can I use the alternating series test? Because there's an alternating sign. So, is that what I did? I don't even remember, but let's eyeball it real quick. If we ignore that changing sign, we take the limit as n goes to infinity of this. It would be infinity over infinity. So, we would need L'Hopital's rule. So, that's what I started doing here. So, okay, I'll get to the end of it. So let's continue with my thought process first. We need L'Hopital's rule, so take the derivative top and the bottom individually. We get this, start simplifying. This half we can pull out. This 1 over n can be an n on the top. Okay, so this is square root n. 1 minus half is half, so n to the half power, which is square root. This is infinity. So the test for the alternating series test would not work. Because remember, the alternating series test says if the sequence is decreasing and it approaches 0, then it converges. It doesn't say anything about diverging, actually. So we can't use the alternating series test to say that this guy diverges. That's not allowed. Okay? Instead, we found this limit, and since it approaches infinity without the changing sign, if we add back the changing sign, it'll oscillate between positive and negative infinity. So the limit doesn't exist in the original guy, and therefore, by the test for divergence, this guy diverges. Okay? So, again, it would be wrong to say this diverges by the alternating series test. The alternating series test doesn't say anything about diverging. It only concludes a possible conversion case with those two conditions. How about this one? This looks really similar to this one, but now it's flipped. So let's try the alternating series test again. Okay? So, again, we're going to find this limit first. We could probably, as I even said here, we could probably make a good guess that as n approaches infinity. Since this approached infinity, if we now flip it, it should approach 0 by gut intuition. Let's prove it. Limit as n goes to infinity of ln n over square root n. Again, L'Hopital's rule. This 2 is a 2 out in front. The square root n is the square root of n above the n here. So square root n divided by n is 1 over square root n. As n goes to infinity, it approaches 0, which confirmed our gut intuition. So we can't use the alternating series test yet. I don't know how picky your instructor is, but there's another condition we had to prove. We had to prove that ln n over square root n is a decreasing sequence. How do we do that? We can take the derivative. Okay. I won't go through all the math here, but you can look at it yourself. If I simplify down to here, this is clearly negative for n is greater than like e squared or something like that. As long as it's negative, starting from some value onward all the way to infinity, then we're good. Doesn't matter that, for example, we can't divide by 0, so n can't be 0. So the sequence starts at 2, by the way. So when it's 2, it would actually be positive. Okay? But after some point, it's negative. I mean, by positive, I mean this derivative is positive. But after some point, it's negative, and it's constantly negative all the way until infinity. Okay? So my point, once again, is as long as it's negative starting from some finite value all the way to infinity, you're good. Okay? So it's decreasing. Now we can use the alternating series test. We proved the two things, the two conditions. So the series converges. Okay? This one also looks quite similar to this one. Does it converge? does it diverge? Okay, so can we do something similar from what we just did? Can we do a comparison test even, is what I'm thinking of right now. Because if this is smaller, let's get rid of that changing sign first. If it's smaller than this, because this converges, something smaller must converge as well. Again, ignore the alternating sign. Is that why I did? I don't even remember why I did. So I guess I did alternating series test again. So you can just do the alternating series test again. So n squared square root n, you can rewrite as n to 2.5 power. So go through the motions of finding that limit, it's 0, and then take the derivative of this guy. Is it decreasing? It is after some points. So you can go pause the video, go through the work if you need to. So therefore, it converges by the alternating series test. So this is one way to do it. The other way I was thinking is, well, I can do a comparison test, and that might work as well. So if you're not comfortable with comparison tests, which honestly, it might be quicker if you're comfortable with it, then you can go through the motions and do alternating series test again. You can see it's a little bit of work, but it's not that bad. So similar to the integrals and knowing which technique could be more efficient, similar for here. So, certain test for convergence / divergence might be more efficient than another one. Okay, this one just says use the ratio test to prove that this series is convergent. If they didn't say use the ratio test, I would have used the ratio test. Why? Well, there's a factorial. The ratio test is good at getting rid of factorials. Okay, so be super careful with your notation, is what I put. So we go through the motion ratio test. Limit as n goes to infinity of a sub n plus 1 divided by a sub n. So wherever there's the n, replace it with the n plus 1, and then multiply by the reciprocal. Okay? So why did I say be careful of the notation? Be careful of the parentheses. So this over here, if you replace the n with n plus 1, you need parentheses, so it becomes 2n plus 2. Okay? And 2n plus 2 is 2n plus 2, 2n plus 1, 2n factorial. Okay, so these 2n factorials would cancel. Now you're left with this over here. Okay, now what do we do from here? How do we evaluate this limit? Well, if we have somehow combined these. Okay, so I combine these two first. So I'm thinking like, if I combine this with these, so by distributing, then we can do the degree test. Okay, so I only care about the biggest degree, so I really don't care what's afterwards. So the biggest degree in the top would be n to the n plus 1 power. Okay, and the biggest degree on the bottom would be n, or the biggest degree I'll just say is n to the 2 plus this n over here, or n to the 2 plus n to the n, or let me use more proper terminology, my bad. Okay, if I expand this out, the top out, the biggest power would be n to the n plus 1. I don't care what happens afterward. Just imagine if it's a squared there. Isn't the biggest term n squared? If it's a cube there, isn't the biggest term n cubed? So the biggest term would be n to the n plus 1, the biggest degree term, I should say. Again, to be more precise. Now the bottom, if I distribute this to each term, the biggest degree term is n to the n plus 2, and there's still that 4 out in front. Now do the degree test. The degree at the bottom is clearly bigger, so this limit will approach 0. Okay, which is clearly less than 1, so this converges by the ratio test. Okay, hopefully that made sense. Again, be careful with your notation for this one. So what can we denote about this limit? So notice that this is matching that. Since this series converges, this limit must be 0. Okay? Remember, if this limit is not 0, then for sure the series diverges, but it says it converges by the ratio test, right? So that cannot be the case. But if this limit equals 0, then there's a chance for the series to converge, and it does converge by the ratio test. So whenever the series converges, the limit of the sequence must be 0. moving along. There's a lot of problems because this is a big topic, an important topic for this class, if you're taking Math 2B. Determine whether these are convergent or not. Again, okay, so this one, whenever it's a rational looking like function, it's a good idea to use the limit comparison test. You can go watch the other video if you need more examples. The technique is pick the biggest degree on the top and the biggest degree on the bottom. Don't care about the coefficients. The coefficient is just 1, but if there are coefficients, you don't really need them. Okay, so this simplifies to 1 over n. We know this diverges because it's a harmonic series. So now we do the limit comparison test. The limit is 1, which is finite and positive. So since this guy diverges as well. Okay, I'm going a little quick because I said I would. Okay, next. This one, I would use the ratio test here. Most of the clue is exponentials. Okay, go through the motions. So again, you can pause the video. I'm going faster now. The limit is 1/3, which is less than 1. So the series converges by the ratio test. Actually, it absolutely converges, if you want to be precise. How about this one? Well, it's the series to the n power, so I'm thinking root test. So we go through the motions of the root test. The limit is 1/3, which is less than 1. The root test is the same conditions as the ratio test, so it's convergent by the root test, sorry. How about this one? This one, the limit as n goes to infinity of this guy is clearly not 0. Test for divergence. So it says this diverges. Okay, so notice how even I didn't remember my answer, I was able to eyeball it real quick because I'm thinking I should immediately take limit as n goes to infinity as like the very first step. Unless there's something more obvious like factorials in the other one or exponentials, then I would be thinking other stuff. But if it's something that I'm not quite sure, it doesn't look too familiar like this one, immediately think test for divergence first. Try it out. This series, okay, is it convergent? Justify your answer. I'm thinking it's divergent right away just by experience. But we can do a limit comparison with 1 over square root n, which we know diverges since it's a p series with p equals half, which is less than 1. Okay? So if we take the limit as n goes to infinity of the ratio of these two sequences, so as just an algebra, to rewrite it like this, this limit as n goes to infinity is 1, which is finite and positive. Since this guy diverges as well. Okay, is the series absolutely convergent? Justify your answer. Well, it diverges, does it not? So how can it be absolutely convergent? Actually, not true. My bad. If it's absolutely convergent, then well, something can be conditionally convergent. That's what I'm trying to say. So ignore that. The last few seconds. Okay. Is it absolutely convergent? Well, if we take the absolute value, isn't it the same? This is always positive, is it not? For n is equal to 0 and onward. So not absolute convergent. Not even conditionally convergence, actually. And it doesn't even ask that. Okay, number 6. There's a number 6 here. Test this guy. I'm guessing there should have been an n here. For convergence or divergence, justify your answer. So, how do I know to use the integral test? I see a clear substitution I can make. So, to use the integral test, it has to be a positive decreasing sequence. It's positive. I didn't write that. So I should write that. N greater than E, let's say. Okay, it's positive for n greater than E. And then take the derivative, it's negative for n greater than E, so it's decreasing, okay? Ignore that there's two equal signs there. Or I should just scribble it out, okay? Do the integral. You can make the substitution, and I don't know why this is not showing up. Okay, let me fix it. Should be ln 2. ln 2, ln 2. Okay, so it converges because the integral converged. Okay, sorry if you heard me drinking some water just now. Need a water break. Moving along. Again, there's lots of problems because this is an important topic in this class. This is actually, let me peek how many problems. 9 problems, or 10 problems. Okay. Number 7. Okay, I'm just not going to cover it up anymore. Let's speed this up. Find the limit of the sequence. Well, we find the limit of this guy is indeterminate because it's 1 to the infinity. So how do we do that? We got to take the log. Okay. Use properties of logs. Move that out in front. Okay. Now limit as n goes to infinity. This, well, it's infinity times 0 right now. So we still got to make it a fraction first. Like that is one way. Now it's 0 over 0. So now we can use L'Hopital's rule. You need to chain rule. So be careful. Okay. If we go through the math, the limit should be 3. So therefore, the limit of the original guy, because remember this limit of 3 is for ln of y. So we got to exponentiate it back. So it's e cubed. Okay? Now test this guy for convergence or divergence. Justify your answer. Clearly, since this limit is e cubed, which is not equal to 0, the test for divergence says the series must diverge. As easy as that. Jumping to number 10 instead. Determine whether this series converges or not. Again, this looks like a rational function, so it's a good idea to use the limit comparison test. How do we use the limit comparison test? We pick the biggest degree on the top and biggest degree on the bottom, n cubed. You choose that to be a series, which simplifies to 1 over n squared. We know this converges since it's a p series with p equals 2, which is greater than 1. Okay? I think I said this in an earlier problem. The coefficients don't matter. You don't need to move them in here. You could if you want to, but you don't need to. Now we take the limit as n goes to infinity of the ratio of these two series. Okay? Dividing by 1 over n squared is the same thing as multiplying by n squared. So on the top of this, I'm going to multiply each term by n squared. Now we take the limit as n goes to infinity. It is 3 over 2, which is finite and positive. Therefore, since this guy converges as well by the limit comparison test. Okay. How about this one? Again, I see it. I'm not sure if we did this one actually, but again, I see an obvious substitution. So I'm going to decide to use the integral test. There are 2 conditions that need to be met. This sequence needs to be positive. Okay, which I said here is greater than 0 for n is greater than e. Again, it just has to start at some point. Actually, when it's n equals 2, it's negative, I believe. It might be negative if ln of e is 1. It might not be negative, but it could be. I don't know. See, even I don't know. So to be safe, I know for sure that 1 over n times ln n is for sure positive starting from n is equal to e and onwards. So as long as it's positive from some point onward all the way to infinity, you're good. Doesn't matter if there's a finite number of terms in the beginning that are negative. Doesn't matter. Similar for the derivative. It needs to be decreasing from some point all the way onward to infinity. It doesn't matter if there's a finite number of points where it's increasing, or maybe it's decreasing, increasing, switching. Doesn't matter. As long, again, from some point onward to infinity, it's decreasing, you're good. So we go through the motion to find the derivative, and I found that it is negative when n is greater than e. So it's decreasing at least from e and onward. Now we perform the integral, do the substitution. And when you evaluate the integral, it diverges, so the series diverges as well by the integral test. Okay, this one is a factorial, so okay, let me block the other ones. Clearly, a good idea is to use the ratio test. Go through the motions of all that. You find that the limit is 0, which is less than 1, so this absolutely converges, which means it converges. Okay, so I went through that one quickly. Again, the key point is you see the problem and there's a factorial, so it's a good idea to use a ratio test. This one is alternating series, so maybe it's a good idea to use the alternating series test. Okay, I do the easy part first. As always, limit as n goes to infinity of 1 over ln of n. That's clearly 0. If it's not 0, by the way, you can use the test for divergence to prove that it's divergent. I did that in the other problem, if you remember. So the easy part's done. Now we got to show that this sequence, 1 over ln n, is decreasing. How to do that? Derivative. So I don't know why things are missing here. It should be ln of n, and this should be n over here, okay? So again, it's negative for some point and onward all the way to infinity. So it converges by the alternating series test. How about this one? Again, the clue is there's a factorial ratio test immediately. Let's try that. You find the limit, it's 0, which is less than 1, so it converges by the ratio test. Actually, absolutely converges, which means it converges. Oh, and that's it. Actually, not that's it. One more. This was one of the ones I skipped, actually. I thought this might be a good problem to think through. I honestly would not expect this on the math to be final, but again, it's possible they could ask this, because this was in the previous course. And if you're watching this video for a different class, this might be good practice for your class as well. So the question asks, find all values of p for which the series this guy converges. Okay, how in the world would we do this? Well, let's go with intuition first. If p is -1, then it's n over 1 plus n squared. Hopefully, from experience, you know that that series would diverge. You can go through the work of doing the limit comparison test. You would compare it to 1 over n and all that stuff. Okay, so I won't explain all the details here. You could work through it yourself, but from experience, hopefully, you know that that series would diverge. And if p is less than -1, so this 1 plus n squared is on the bottom of the fraction, and it's being exponentiated at the bottom of the fraction to some bigger number, the series would converge. Again, you can go through the motion of the limit comparison test to prove that, probably. That's just my intuition. So again, hopefully I'm hammering in the points that if you've done enough problems, you would have such intuition like this to answer this maybe more challenging problem. Okay? So the professor probably wanted a more rigorous proof or better logic work shown on the exam than just simple intuition like this. So how did I do it? Again, I don't have the answer key for this, but this is how I thought through it. Let's assume that this sequence is decreasing. If it is, well, this is for sure positive. I don't need to question that because n is equal to 1. N is starting from 1. It's going to be positive. So I'm just going to assume that the sequence is decreasing. If I can assume that, then we can use the integral test. Maybe that can help us, because I see maybe we can do a substitution, actually. There's other ways probably you can solve this, like if you actually do a comparison test or something like that, you could probably solve it as well. But this is what I thought of. So we're going to do this integral from 1 to infinity, n times 1 plus n squared to the p dn. So p is some constant, okay? And I'm using the proper notation here. So now let's make the substitution. U is 1 plus n squared, du is 2n dn. So this becomes u to the p, and n dn is half du. Okay? And the limits of integration change. Be careful. Technically, it doesn't quite matter here, but let's be careful with it. Or it might not matter. It might. I don't know. I probably did it, so I don't know. Anyway. Here we just use the power rule. We're integrating with respect to u. Okay, so this is just some constant. We're just going to use the power. Increment the power, divide by the power. Okay, evaluate from 2 to 1 plus t squared. That's fundamental theorem of calculus. You go through the motions. That's this line. Okay, for this limit to exist, which means the integral converges, and hopefully we can use that. If the integral converges, the series converges as well by the integral test. So this is just some constant. We're fine there. We need this limit to exist. Okay? And that happens if p plus 1, this power, is less than 0. Okay? And we solve for p. P is less than -1, which matches my intuition in the beginning. Okay? So again, I don't have the answer for this. This is how I thought through the problem. If it's not correct, please let me know in the comments, and I'll be more than happy to do a follow-up video if I understand what's going on. Okay? Now this is the end of the video. Hopefully this is good practice for you if you were looking for additional practice. Otherwise, I hope it was also good to just see the types of problems that could get asked, especially if you're taking the Math 2B class at UCI. Again, these were problems from the old class, the problems from possibly past final exams from the old class. So it's likely that they'll ask similar types of questions, if not very, very, very similar, of similar difficulty as well on the Math 2B final exam. Okay, so if you are still struggling, I would recommend practicing a lot more. So you can see that if you practice a lot, you have such intuition like this to get some of the maybe harder ones as well. All right. Please like and subscribe as always if you found this helpful. And hopefully I see you in the next video as well. Bye.